was the question?
Well, the original question is sigma infinity and n equals 1, and then n over n squared plus 1. And I understand how to get to, like, I don't understand the continuous positive and decreasing things to be able to claim the integral test is what you're supposed to do. Or do we not have to worry about that?
I don't think you need to worry about that here, because I believe in this case you can just directly use it.
You can, but it's in the watch it video. It said it's because it's continuous positive and decreasing from 1 to infinity. But why is that?
That is just looking at this part. This an, if you just look at that function is it's always positive, right? Because for n is positive, you always have a positive value. It's always continuous because it doesn't matter which value, so always positive, and always continuous, because the only value that will make the denominator 0 is when n equals I, but we're not considering imaginary numbers here, right? And is it always decreasing? You can try to find out by finding the difference between the an and the an plus 1. If you carry out the process, it's always it's going to be a positive value for all n. That's from 1 to infinity. Finding the common denominator there. Well, it's probably better to rewrite this. So n squared plus 1 times n plus 1 squared plus 1. Common denominator, the first numerator is n times n plus 1 squared plus 1 minus n squared plus 1 times n plus 1. And if we were, the denominator is always positive there. If we were expanding the numerator, I'm going to do it a bit quick here. So that's n times n squared plus 2n plus 1. That's an n cubed plus 2n squared plus n plus another n, that's plus 2n, minus, when we follow the second product, you get n cubed minus n squared minus 1. Another numerator going to be n cubed cancel, you get n squared plus n minus 1 divided by the denominator. So for n that's greater or equal to 1, the numerator is always positive, the denominator is always positive. Therefore, it's always the difference, it's always positive. So it's always decreasing. So that's a reason that that's always decreasing.
And how did you know that top fraction at the bottom was n minus 1?
Say it again.
How did you know that top fraction at the bottom, the n squared plus n minus 1, was positive?
This expression, so keep in mind that n is from 1 to infinity, right? So the smallest
okay.
n equals 1. So if you put 1 there, you get positive, but when you put that, it's more positive, right?
Okay. Yep.
Yeah, I don't think you really need to get into the details if you try to use the integral test, because
but off that, do you want us on the exam, like if we have to do the integral test, like explaining all 3 of those things, or are you okay?
No, I wouldn't. I would say just, start with the integral test.
Okay.
That should be plenty of work. but maybe I'm not being, precise here, but so if we give you a question that we expect you to use integral test, that means the function we give will be continuous, positive, and decreasing. We will give you a tricky question. All right. Good question. All right. I don't know if you have any other questions or someone else have questions. I'm not hearing any questions, so I'm not sure if you don't have any questions or you just shy from asking questions. But I have one I want to, well, I have a couple of things I want to point out. Maybe you find it helpful. The first one in the homework, that was a question Sam asked was like, I think it was like a 5 to the n plus 1 times 6 to the n negative n. So to the previous question, what was the final answer? I don't know what the final answer was. So if you use the, anyway, let me finish the previous problem and then move on to this example. So the previous example, previous problem, I think so obviously you can try to use divergence test by taking the limit as n goes to infinity of n over n squared plus 1. That's going to be 0, so that's inconclusive. So that doesn't work. And it doesn't look like it's a 1 over n to the p. So you cannot use p series test, right, by just looking at the an formula. And it's not the geometric series, so cannot use the geometric series for that case, or geometric. So what we end up with will be the integral test or the comparison test, right? So you probably think, how about comparison test? Well, the direct comparison test, by just looking at an, we know that n over n squared plus 1, if we drop one term in the denominator, we get a bigger value. So that's going to be less than or equal to n over n squared, which is just 1 over n, right? That's one function that's less than the series that's given. So you probably consider to use the 1 over n. So this is like a direct. So it means the series n over n squared plus 1, this given one, is less than or equal to the series 1 over n. And if we were to look at this series, that this is a 1 over n to the p is 1 there. So p equals 1, it tells you that this series on the right is divergent. Well, that's not very helpful. It just tells us that the bigger series is divergent. It doesn't say anything about the smaller one, right? The one that we are interested in. So this direct method doesn't help. But how about the limit comparison test? I don't know if it works, but I'm just going to try, sort of try try them one by one. So the one that I give is this one, n over n squared plus 1. I'm going to call this bn. There was Sam asked a good question during office hours. It really doesn't matter. You could call this an. Doesn't matter which one is an, which one is bn. At the end, it's going to work the same way. because all we're interested is C. I'm going to write down in a second. We want to know if C is positive or negative, right? So the new one, so the new series we pick to compare is, I'm going to use the leading term of the numerators n, the leading term of the denominators n squared. So that's just the series 1 over n. It didn't work in the direct comparison test, but let's see if it works here. So define C is equal to limit n goes to infinity of, so this part I'm going to call it an. Like I said, it doesn't matter which one is an or bn, it's the same. So 1 over n divided by bn, n over n squared plus 1. So that's going to be limit 1 over n times the reciprocal, n squared plus 1 over n, and it goes to infinity. And if we carry out this multiplication, we just have limit n squared plus 1 over n squared. Right? And I hope that at this point, you're just looking at it, you know what the limit is. It's just 1. Right? So this tells us the C value, it's positive and it's finite. So that's a good thing, right? We want it to be positive and finite, because when it's positive and finite, we know from C equals 1, we know that both the series, the one with an and then the one with bn, so we know that this n over n squared plus 1, and the second one, the new one, 1 over n, will behave the same way, will both be convergent, or both are convergent, or both are divergent. We just don't know which one it is, right? So that's a good thing, one step closer. So the last thing is that we have two series. This one is what we want to know. This one is a lot easier to find. So let's just focus on this one that's easy to find. Sigma 1 over n for n from 1 to infinity. Based on our experience earlier, we know that we can use a p-series test. So this we know is divergent. Since both of them behave the same way. Right, you can use it directly, but I'm just showing you this like two different methods, right? The first one is to use the direct comparison test. We found out that the series 1 over n is divergent. This one is I'm using the limit comparison test. If we just look at the limit comparison test, we have to, use the series 1 over n is divergent. If that's divergent, both of them are divergent, or both of them are convergent. Therefore, this one we want to know has to be divergent. Right. So that's a limit comparison test, even though the direct one didn't tell us anything. You could also try to use the integral test, which is you take this series, right? And then you find out the integral from from 1 to infinity of n over n squared plus 1. X over x squared plus 1 dx. This is a improper integral. If you want to find the value, if you want to find the evaluate this, you have to rewrite it using the limit definition, which t goes to infinity, 1 to t x over x squared plus 1 dx. And I believe you should be okay to find the antiderivative by letting u be the denominator. So if you use u equals x squared plus 1 du equals 2x dx, and then substitute in there. So dx equals 1 over 2x du. And it shouldn't be too bad, I think. So limit integral 1 to t x over u times 1 over 2x du. So x cancels. And you get 1/2. You can bring the 1/2 in front. So 1/2 limit integral 1 over u du. That's just natural log. Absolute value of u. If x is evaluated from 1 to t, right? If you carry out this, so that's a 1/2 limit natural log of u is what? U is x squared plus 1. I'm going to put it here. That's not correct way, but that's a natural log absolute value of x squared plus 1. Evaluated from 1 to t. And if you carry out the process, t squared plus 1 minus natural log of 1 squared plus 1, that's a 2. And take the limit as t goes to infinity, you should end up with infinity. Right. So the infinity at the end tell you that the improper integral is divergent. Therefore, the series that we are interested in is also divergent. So the good things about this particular example is that both tests, the integral test works, also the limit comparison test works. On the exam or on homework, you might have a problem that you try one test, it works nicely. You try another one, it also works, but it just takes a little bit longer. All right, any questions on that example? So I just want to go through the tests that you probably will need on the exam. All right, so let me go through this quickly, then I'll let you ask your question, please. So this is a homework question. So when you see something like this, the first thing I notice that I see that 5 is raised to the power n, and the 6 also raised to a power of n, but it's negative, right? So what I'm going to do is I'm going to rewrite this expression by splitting the 5 to the n plus 1, write it as 5 to the n times 5 to the first power. And then 6 to the negative n, I'm going to write as a 1 over 6 to the n, so divide by 6 to the n. The benefit of doing this is that now I have the 5 to the n and the 6 to the n, I can combine them because it's 1 in the numerator, 1 in the denominator. So that will give me 5 over 6 to the power of n, right? And then I have an extra 5, so I'm just going to put a 5 on the side. You can put it in front or put it at the end, but it doesn't matter. So now by looking at this series, this looks like some a, constant a, times r to the power of n form. So the r is a ratio of a geometric series. So what this tells us that what we have here is a geometric series. And then the I is equal to 5 over 6. And then based on this value, we know that that's less than 1. So the geometric series is convergent. And if we want to find the sum, so the next part is to find the sum. Here you have to be a little bit careful. For geometric series, if it's convergent, we know the sum is equal, so sum is equal to a over 1 minus r. All right, that's a formula we use. But you have to be very careful. This a here, this means the first term in the series right? And this A I wrote in the side here, this A is not the first, the way I'm written is not the first term. This A is just a constant. They're not the same, so be careful. That's why I want to point this out. So if you want to find the sum, you have to go back to the series. Doesn't matter which one you use. You can use this one or you can use this one. Doesn't matter which one you use. You have to figure out what the first term is. Well, how do we find the first term? We know that n is from 1 to infinity. So you just take n equals 1, put in there. So to find A, just take 1, put into the either form, you get 5 times 5 over 6 to the first power, you get 25 over 6. That is the first term we need for the sum formula. And I is the same, the ratio doesn't change. So use that for A, so you get 25 over 6. Divide by 1 minus 5 over 6. So that will be 25 over 6. The denominator, if you common denominator and subtract, you got 1/6. So divide by 1/6 times 6, so you get 25 at the end. All right, I'm pretty sure you all know how to use the sum formula, but I want to clarify that this A here is not the same A, it's not 5. So let me erase that. So A, it means the first term in that series after you plug in n equals 1, what you get. Of course, if the sigma is from, let's see, you have a sigma, let's say from n equals 3 to infinity, or n equals 5 to infinity of 5 over 6 to the n, then you take 5, put in there. So first term in the sum formula, so this A here is equal to, take 5, because, sorry, I probably should use, let me use 10 here for n from 10 to infinity. So you'll be taking 10, put into the expression, so that's 5 times 5 over 6 to the 10th power. So that's what the first term is. So be careful when you find the sum. You know how to do it. I mean, no big deal. You know, if you get it wrong, I probably take a point off, but I just want to clarify that. That way, you're more prepared. Okay, Chris, what's your question?
It was the sum from 1 to infinity
Mm-hmm.
of 3 over n squared plus n cubed.
This one?
Yep.
Good. So this one, again, if we use the divergence test, you get 0, so we cannot conclude anything. It's not the P series test. It's not the geometric series. So I'm going to try with comparison test. Right. So I'm going to take 3 over n squared plus n cubed. So here we have 2 terms in the denominator. Both are positive, right? Because n is positive. So n squared is positive, n cubed is always positive. So I can just drop any of them. It's just like we did with the plus. I think earlier we have a plus a number at the in the earlier example, we just dropped them. So here, so this function is going to be less than or equal to 3 over n squared. It's also going to be less than or equal to 3 over n cubed, right? It doesn't matter which one you use. At least one of them should work here. I'm going to use this one first. So if we run into problems, then I'll try the other one. It doesn't matter. So that means the series given 3 over n squared plus n cubed is going to be less than or equal to the series 3 over n squared. And this one, even though you have a 3 here, that doesn't matter. We can always bring it outside and leave it a 1 there. So that will be series 3 times series 1 over n squared. And this part, this series, you should be able to figure out it's using the p-series test, which we know it's convergent because p is 2, which is greater than 1, so convergent. Even if it's convergent when you multiply by 3, it should still be convergent. If you have a series, the sum is finite, even though you multiply by 3 or 100, one finite number times a finite number is always a finite number, right? It's not going to, if you take two numbers you already know, you multiply them, it's not going to go to infinity. That's what I meant. So that's convergent. Therefore, this one, when we multiply by 3, it's still going to be convergent. The one we are interested in is less than this series. So if it's less than the convergent series, it has to be convergent. So that's using the direct comparison. It's a little bit easier. But if you didn't use this, you can also use the limit comparison. Or I don't think an integral has this easy. But if you want, you can use limit comparison test. You can say, okay, the given one, you can call this Bn, and then the new one that we pick is just going to be the leading term of the numerator is 3. The leading term of the denominator is n cubed. So we're going to call this An. And then we can define the C, which is the limit n goes to infinity of An over Bn, which is 3 over n cubed divided by 3 over n squared plus n cubed. If you simplify this and then carry out that process, it should give you a positive finite number. Right, so I'm going to leave it there. So that means they behave the same way. Then you take this new one because this one is a lot easier to find convergence. It's actually convergent. So, all right, any other questions? So I would say for comparison test, the direct comparison test, if you have, or even for limit comparison test, if you have a series that's have multiple parts in the numerator, it could be subtraction there, doesn't matter. Or if you have multiple parts in the denominator, when you have something like this, you probably can get the conclusion easily by using comparison test. That's what I think will work. If it doesn't work, try other ones, right? But that would be something to try. Or if you have something like, you might have like a sine to the, doesn't matter, 100 n to the 100th power or something, divide by maybe just n to the 6 or something like this. When you have a sine and a cosine in a series, it's also a good idea to use comparison because we know that sine or sine squared, doesn't matter, right? But we know that sine is going to be between, doesn't matter what it is, here it could be, any n1 to the 100 or something, right? Doesn't matter what it is, that's always going to be between 1 and a -1. So that's always for sure. So if you have the something like the example I gave you, sine of n to the 100, that divided by n to the 6 is always going to be less than or equal to 1 over n to the 6, greater or equal to negative 1 to the n to the 6. That is just for sure, we know that because because sine is always going to be between those two values. Same thing with cosine, right? So if you have sine and a cosine and you don't know what to do with them, it's good to try with comparison test. It may not work, right? You might have examples that the comparison test doesn't work. In that case, try another method. Okay, I think I've done enough talking. I don't want to take too much of your time. Any other questions before we move to the exam?
Just to clarify, you said cosine is also between -1 and 1?
Correct. If you just have cosine, doesn't matter what the part inside the cosine is, right? It could be like an n to the 100th power or 100 to the nth power. Even though it could be a really big number inside cosine, the cosine value itself together, right? The cosine value is always going to be between 1 and -1.
Awesome, thank you.
Yep. And I didn't write down like a sine squared. Doesn't matter what this part in the parentheses is. It's always going to be from 1 and a 0. Because you basically square the numbers from -1 to 1. So the biggest you get is a 1. The smallest is 0. Same thing with cosine squared. It's always between 1 and a 0. So if you see them, that will be a good idea to try comparison test. I'm not saying it's always going to work, but it's good to try. All right. Any other questions? I noticed that I'm taking too much time doing the review. I'll give you, just like before, you have, so maybe let's see, we start from 6:45 if you don't have further questions. And then we have 1 hour and a half, 90 minutes to work on it. And then 10 minutes after that to upload your work. Any questions before I make the quiz available? Just do your best. There will be questions that asking you, determine if the series is convergent or divergent. Make sure you show your work, right? Don't just say, oh, it's convergent and move on. You have to show the correct work. Do your best. That's if you don't show the work, then I don't know, you have a good reasoning for the answer you provide.